So let's look at the physical pendulum now. So a physical pendulum is just any object, so which has, let's take a random shape for now, that is hanging from a point. So let's just take this like a blob over here, right? And so let's say that it's hanging from this point, and then let's say that there is a center of gravity for this mass. So let's take, so the mass is gonna, weight is gonna act on the center of gravity, right? So this is the weight of the object, and then this is this distance is gonna be d, right? The distance from the pivot point to the from the pivot point to the center of mass. So now the derivation is similar. The way I did it for the simple pendulum, this is similar. So again, this distance is d. So the net torque acting on the physical pendulum is I times alpha, and then this is, so now again there are two components of weight, right? This one is the restoring one, right? So this one is W sine theta. So we're assuming that this angle is theta, right? So this angle is also theta. So this is W cosine theta. Okay, so now W sine theta is the restoring force, and so that's mg, W is mg sine theta, and then times d. So this is again the torque due to the force, and so so this distance is d, and then this is the force F perpendicular, and so that's equal to I alpha. And I'm going to flip the equation again, so you get alpha equals minus mg d divided by I, and then sine theta. Now again, that same argument that I used for the pendulum, that we're looking for small angles now, because if you write this equation, alpha is d2 theta by dt squared minus mg d over I sine theta. This doesn't look like a simple harmonic motion equation, so so this is going to be a simple harmonic motion for small angles, and for small angles sine theta is approximately equal to theta, so this is called a small angle approximation. So now we get d2 theta by dt squared, and then minus mg d divided by I times theta. Now now this is the equation for an object undergoing simple harmonic motion, and so this again has units of 1 over frequency squared, right? You have theta does not have any physical dimensions, and so you have 1 over second squared over here, and so this factor should have units of 1 over second squared, and so therefore we'll call it omega squared mgd divided by I. So that's omega squared, so we can take the square root of that, so we get square root of mgd divided by I. So frequency of the physical pendulum would be, omega divided by 2 pi, and so 1 over 2 pi square root of mgd divided by I. And so time period is 1 over frequency. Okay, so that gives you 2 pi square root of I divided by mgd. So that's the equation for the time period, and again I is the moment of inertia of the object around that pivot point. So we can use this equation to, for example, so let's say you want to get let's do that. So let's say you want to get the time period of let's say a rod hanging from let's say from one of its corners. So let's say this is a rod. Okay, so remember the like a ruler or something, right? So remember the moment of inertia around the end is 1 over 3 ml squared, and we discussed this in the rotation chapter, right? So now if you so the weight is going to act at the center of mass. So the center of mass in this case is at a distance L by 2, right? This is your weight, and so D, in other words, is L by 2. And so the time period when you plug that in, so it's 1 over 3 ml squared, and then mg L by 2. And so the mass cancels out, one of the L's cancels out, and you get 2 pi times square root of 2 by 3 L over G. So that's the time period of a rod hanging from its thin rod hanging from one of its corners.